Hi guys, how are you? I hope you are doing well. So today we're going to talk about section 15.2, that's double and triple integrals over general regions. So in section 51 we discussed double triple integrals over rectangles. So let me just remind you. So if you have, let's say, a double integral, let's say f of xy, and then you have dx, dy, x between a and b, y between c and d. So again here, that means your x, so your x is between a and b. So x is between a and b, and y, your y here is between c and d, right? So y between c and d. Right, and let's say now we want to graph the region which corresponds to x between a and b and y between c and d. So let's say here is your x-axis, this is y-axis. Let's say here is your a and b, right? So when you say x is between a and b, it means the points between the lines x equal to a and x equal to b. So here, this is the line x equal to a. So this is x equal to a. This is the line x equal to a, and this is the line x equal to b. So when you say x between a and b, it means the points between the lines x equal to a and x equal to b. So that would be this region here. That's the set of the points with x between a and b. Okay, so it's between the lines x equal to a and x equal to b. Now, when you say y between c and d, so this is c, this is d, so this is the line. So this is y equal to c, and this is y equal to d, equals to d, okay? So when you say y between c and d, it means that the set of the points between the lines y equal to c and y equal to d, okay? So now, what will be the intersection? So what would be the intersection of the blue and the green regions? Well, so the intersection, it will be this rectangle here. So we get this rectangle, right? We get this rectangle, and that will be our rectangle of integration here. So this is our rectangle. So that's why, right? So that's why when you say x between a and b, y between c and d, you get this rectangle. Okay, it's because it's the intersection. It's the intersection of the two regions. The first region corresponds to the region between the lines x equal to a and x equal to b, and the second region is the region which corresponds to which is between the lines y equal to c and y equal to d. Right. Now, what I'm gonna do, so here, I got a rectangle because I have lines, straight lines, right? X equal to a, x equal to b, and then you have the straight lines y equal to c and y equal to d. Now let's say instead of lines, I'm gonna use a graph of functions. So let's say you have, so again here's x, this is y. Again, let's say x is between a and b. So here's a and b. Okay, so here, so this is x equal to a, and this is x equal to b. Okay, so here x is between a and b, right? So that will be this region here between the two lines. Now, for y, instead of taking lines, y equal to c and y equal to d, I'm gonna take y equal to some function. So let's say y, so let's say here you have this function f1 of x, or let's say g1 of x, okay? And I'm going to take another function, let's say g2 of x. This is g2 of x. Okay. So when you say y is between g1 of x and g2 of x, it means that the height y is between the graphs of the two functions here, g1 and g2, right? So it's going to be this blue region here. That's the region between g1 of x and g2 of x, right? Now, what will be the intersection between the blue and the green regions? So the intersection would be this here. It will be this region here. And of course, it's not necessarily a rectangle, right? I mean, it depends on the graphs of G1 and G2. Okay, so this is not, of course, this is not necessarily a rectangle. It could be anything here, okay? So that's what I mean by a general region. So it could be any random region, okay? So then the corresponding integral, so we're gonna integrate over this region here, and when you integrate over this region, so then your integral should be of the following form. So you have the function f of xy, but then here you need to be careful. So your x is between two constants, a and b. Your y is between the two functions, g1 of x and g2 of x. So what we do here in this case, if your y is between two functions and your x is between two constants, so first we integrate with respect to y. So y first. So then your y is between g1 of x, g2 of x. And then you put the constant, and then you finish with the constant. So then x is between a and b. Okay, so it's really important here. So the order of integration here is really important. Okay, so you need to start if your x. So what I'm saying here. So this is the case. So your x is between two constants, and your y is between two functions. Okay, so if your x is between two constants and your y is between two functions, so first you need to integrate with y and then with x. So we need to finish. So you need to finish with your integral with the constant here. So you need to put the constant at the end here, okay? So first you integrate with respect to y and then with respect to x. Okay. Now I can do the same. I can interchange x and y. So here, let's say in the case y is between two constants, c and d, and then x is between two functions. And of course, x is going to be between two functions of y. So x is between, let's say, h1 of y and h2 of y. Okay. So let's see the corresponding regions. So I have my x-axis, I have my y-axis here. So I'm saying y is between c and d. So this is c here, this is d, okay? And then this is the line y equal to c. So this is y equal to c, and this is y equal to d. Okay, and so when you say y is between c and d, then that corresponds to this region here between the lines y equal to c and y equal to t. Now x, I said x is between two functions of y. So you're gonna have like something which looks like this here. So let's say this is h1 of y, okay, and this is, let's say, h2 of y. Okay, so here I'm saying x is between two functions, h1 of y and h2 of y. So that corresponds to this region here between the two graphs, the h1 of y and h2 of y, okay? And now, of course, the intersection would be this region here. Okay, and of course it's not necessarily rectangle, okay, right? Because h1 and h2, they could be random functions, so it's just some random region here, okay? And now, what will be the corresponding integral? So in that case, so if this is our region, then so you have to integrate some function f of xy, let's say. Now the order of integration, because x is between functions and y is between constants, so first we start with x. We start with x because x is between two functions of y. So here it's between h1 of y, h2 of y, and then you do y. So y would be between c and d, okay? So again, the idea is, so you have this double integral, right? So your, let's say your y is between two constants and your x is between two functions. So first you integrate with respect to x because x is between functions, okay? And then you do the, you integrate with respect to y. Here, in this case, your x is between constant, right? And y between two functions. So if y is between two functions, then you start with y. So you have to integrate first with respect to y, and then you integrate with respect to x because x is between constant. So first you start with y because it's between functions, okay? So let's do a couple of examples here. Okay, so let's say you want to find the volume of the solid under the surface f of xy equal to x squared y and above the triangle with vertices 1, 1, 4, 1, and 1, 2. Okay. So, first thing here, you want to find the volume of the solid under the surface f of x, y, x squared y, and above the triangle. So, remember guys, by definition, so we have, let's say, here's my rectangle. Let's say this is my rectangle here. Okay, that's my rectangle. And then I have the image of the rectangle by the function f. So it will be something here. I don't know, some region here. Okay, so this is my f of xy. So it will be this region here. This is my f of xy. This is my rectangle. Okay, and let's say, so this point here goes here, this one here goes here, and this one here goes here, right? So we can get this. So that will be our solid. Okay. So it's bounded by the green surface and you know, the blue triangle, right? And by definition, we said that will be this is supposed to be the double integral of f of xy dx dy, or f of xy dy dx. Okay, so we have to integrate this function here, x squared y, right? But the problem is here, we don't know the bounds, so we need to find the bounds here, right? So the question is to find the bounds of integration here, right? So we integrate over this rectangle. It's not over, sorry, we're gonna integrate over this triangle, right? So it's not a rectangle. It's not just saying, it's not like saying x from A to B and y from C to D. It's not a rectangle, so it's a triangle. So let's find, so let's describe Let's describe the region corresponding to the triangle. So so this is my x-axis, here's my y-axis. So let's say here's 1, 2, 3, and let's say here's 1 here and 2 here, right? So my triangle actually corresponds to the following. So vertices, we have 1, 1. So here's the first vertices, right? So first vertex is 1, 1. Second vertex is 4, 1. So I'm gonna need 4 here. So this is 4. So the second vertex is 4, 1. And the third vertex is 1, 2. So that would be this vertex, it's 1, 2. So my triangle would be this one here. Okay. Now, let's see how it works. Now, I want to describe this region, right? So if you say, what will be the bounds for x, for example? Well, you can check your x-axis here. So your x is between, so for this region here, for this triangle here, you can see that your x is between, so here, x is between 1, and the last point here corresponds to x equal to 4. Okay, so you can say x is between 1 and 4, right? So x between 1 and 4, it means that that's the region between the lines x equal to 1. So this is x equal to 1. This is x equal to 1. And this is x equal to 4. Right. So when you say x is between 1 and 4, it will be this region here between the two lines, x equal to 1 and x equal to 4, right? Of course, you don't get the triangle here. You get, the region between the lines x equal to 1 and x equal to 4. Okay, now what about y? Well, the height y, you can see the height y here. So here's, this is 1. Here it's 2. So if you say y is between 1 and 2, so then it means it will be the region between the lines y equal to 1 and y equal to 2, right? This is y equal to 1 and y equal to 2. So it will be this blue region, right? Between the lines y equal to 1 and y equal to 2. But then, what will be the intersection? Well, the intersection is going to be a rectangle. So it won't be our triangle. So it's going to be this rectangle here, right? It's going to be this rectangle. And we don't want the rectangle. We want this, the half of the rectangle. We want this red triangle, right? So we cannot say, I mean, if you want to describe this, the region inside our red triangle, I mean, we cannot just say x between 1 and 4 and y between 1 and 2, okay? So what we can do in this case? Well, so we can say, well, instead of saying y between the lines y equal to 1 and y equal to 2, so let's say first, well, y here between 1, so this is the line y equals to 1, okay? And then, instead of using the line y equals to 2, I'm going to use this line here. Okay? So I'm going to use this line here. Okay. So now, what will be the region, let's say, between y equal to 1 and y given by this line here, this one here. So this line here and this line here. So you can take, if you take this region between these two lines, this region here, this one here, right? Let's say this region here between the two lines. So what will be the intersection now between our the green region, which is x between 1 and 4, and our blue region? Well, the intersection now is going to be exactly our rectangle. So it's going to be this region here. So that will be the intersection between the green region, between the lines x equal to 1 and our blue region. Okay. Now, what's the equation of this line? Well, this line here passes through the points, the vertices 1, 2, and 4, 1. So the equation of the line, so the line passes through 1, 2, and 4, 1, right? So, guys, in general, the equation of a line would be y equal to ax plus b, right? So here I'm saying, so if x is 1, y would be 2. And if x is 4, y would be 1. Okay, so we have two equations here. So we have 2 equal to a plus b, and 1 equals to 4a plus b. Okay. If you take the difference between the two equations, this is first equation, second equation. So 1 minus 2, let's say, then you're going to have 1 equal to minus 3a. So a would be negative 1/3, and if a is negative 1/3, then b would be, so then b would be 7/3. Okay. So what I'm saying, guys, is that the equation of this line here, so this is the line y equal to minus 1/3 of x plus 7/3. Okay, so actually my x is between 1 and 4, and my y is going to be between negative 1/3 of x plus 7/3. Okay, and so the integral now, so I remember we have my function f of xy. So f of xy is this function here, x squared y. So here I'm going to have x squared y. Now the region is x between, we said x between 1 and 4, and y between 1 and negative 1/3 x plus 7/3, right? So that's our region, which describes, so these two inequalities actually describe our rectangle, right? So now, do we integrate first with respect to y or with respect to x? You see here, x is between two constant, y is between, constant and a function, right? So we are in this case here, x between constant and y between two functions. So if x is between two constant and y is between two functions, so we integrate first with respect to y. So here we need to integrate first with respect to y. So here we're gonna have y between 1 and negative 1/3 x plus 7/3, 7/3, and then x between 1 and 4. And so we are done. We can just compute our integral. So here, of course, dx. So first we integrate with respect to y. X is a constant, So that will be equal to x squared, y squared over 2. X squared is a constant. And of course, your y is between 1 and negative 1/3 x plus 7 over 3. So because we integrated with respect to y, then you need to replace y by 1 and then y by negative 1/3 x plus 7 over 3. And then of course you need to keep this 1 4 here and this dx. So that will be 1 to 4 x squared. So first I'm going to replace y by negative 1/3 x plus 7 over 3 squared over 2 minus, right? And then you replace y by 1, so that's x squared times 1 squared over 2 dx. Right? And then you can finish your integral, and you can find the details of the computations in the lecture notes. You finish the integral, and the answer actually is going to be at the end. The answer would be 31 over 81. Okay, so here you need more steps. Now, so again, guys, here when I try to describe this triangle, I said my x is between 1 and 4 first, and then I try to determine my y. What I can do also is I can start with y. I can start with by saying that y, so let me again, so here's 1, this is 4, this is 1, and let's say this is 2. Here's my triangle. Okay, so here I said my x is between 1 and 4, and then I determined my y. So now I can say, I can start with y. Let's start with y. So you can say, well, my y first is between 1 and 2. So here, y is between 1 and 2. So this is y equal to 1. And this is y equal to 2. So that will be this blue region here. Okay. Now, what about x? So again, if you say x between 1 and 4, then you're going to get a rectangle. You don't get the triangle. But if you say x is, let's say, between this one here, so x equal to 1, and this line here. So I'm going to use this line here. Okay. So what's the region between x equal to 1 and this line here? Well, it will be this region here, right? And so what will be the intersection between the blue and the red regions? Well, the intersection then is gonna be exactly our triangle. And that's what exactly we need, right? So that will be the intersection between the red and the blue regions. So here, your x, we are saying that x is between 1, and so what's the equation of this line? Well, we know that the equation of this line is, y, we said y is equal to minus or negative 1/3 of x plus 7 over 3, right? So then you can solve for x. So then x, y minus 7 over 3 equal to negative 1/3 of x. So times negative 3. So that's negative 3y plus 7. So that's x. So x will be negative 3y plus 7. So we can say that, so this region here is between, so x is between 1, this red line here, and this line here, and this is the line of the equation of the line. So x equal to negative 3y plus 7. Okay, so now I can compute my integral. So I have f of xy, so it's x squared y, x squared y. Now, do we integrate first with respect to x or with respect to y? So y is between 1 and 2, right? It's our blue region here, right? This is y is between 1 and 2, so this is our blue region here. And x is between 1 and this line here, this one here. So that will be this red region, right? So y is between constant, x is actually between a function. Well, one and a function, okay? So we are in which case? We are in the case, this case here. Y is between constant and x between functions. So if x is between functions, then we integrate first with respect to x. So here we need to integrate first with respect to x. So here's dx dy, x between 1 and negative 3y plus 7, and y between, of course, 1 and 2. Okay. And then you can compute the integral, and of course, you get the same answer. Okay. Okay, let's do another example, guys. Example 2. Let's say you want to evaluate the integral from 0 to 1, and then e to the x squared here, dx, and then dy, x between 3y and 3, right? So here you see, guys, first I need to integrate with respect to x, right? So I need to integrate e to the x squared, right, with respect to x. And actually, I mean, it's not possible to integrate this e to the x squared. Integral of e to the x is of course e to the x plus constant. But integral of e to the x squared, I mean, that's it's not possible to compute this, to integrate. So how can we evaluate such integral, right? I mean, we don't know what's the integral of e to the x squared with respect to x. So the idea here is to change the order of integration. Because if you change, you see, when you change the order of integration, then it's going to be possible to integrate, change the order of integration. So, because if you change the order of integration, so if you integrate first with respect to y, e to the x squared, because x is considered as a constant, because you integrate with respect to y, x is considered as a constant, and an integral of a constant is just constant times y with respect to y, right? So if we integrate first with respect to y, it's going to be possible to integrate e to the x squared because it's going to be just a constant, and the integral with respect to y would be just the constant e to the x squared times y. Okay, so we're going to change the order of integration, but if you change the order of integration, you don't just interchange the bounds of x and y. Okay, it's you have to check now the new bounds for x and y when you change when you change the order of integration. So the question now, what's the new bounds? New bounds of integration if we change the order of integration. Okay, so let's see. So let's try to graph this region. So let's graph So what's this region? So here we are saying y is between 0 and 1. So y between 0 and 1. And x is between 3y and 3. X between 3y and 3. So y between 0 and 1, x between 3y and 3. So here's, let's say 1 here. This is 0, of course. X equal to 3. So this is 1, 2, 3. And then you have x equal to 3y. So which means that y is equal to x over 3. So that would be, so first y is between 0 and 1. It would be this region here. So this is y equals to 1. And this is y equals to 0. So that's the corresponding region, right? To y between 0 and 1. Okay, that's the region y between 0 and 1. That's the blue region here. Now x is between 3y. So we said x equal to 3y. That would be the line y equal to x over 3. So y equals to x over 3. So if x is 0, y is 0, of course. And if x is 3, y would be 1. So if x is 3, y would be 1. So this is our line. This is the line x equal to 3y, or if you prefer, y equal to x over 3. Okay. So what I'm saying is that x is between this line here, this red line, and the line x equal to 3. So where's x equal to 3? Here's the line x equal to 3. So my x is between these two lines, this line here and this one here. So x actually is going to be between these two lines, right? And of course, you can check, you may ask why it's not, for example, this region here. Why it's this one here. Well, you can just pick a random point. For example, you can pick this point here. Oops. You can pick this point. So let's say you pick, this is 1, 2. So you pick this point here. This is the point x is equal to 2 and y is 0, right? So this is the point 2, 0, right? So the question is, does it satisfy this inequalities here? So my x is 2, my y is 0. So is it true that 3 times 0 is less than 2, less than 3? Yes. So it means that this point belongs to my region. Okay, so that's why I take this red region here between these two lines, not this one here, not this one here. Okay, so you can just pick a point and you check that the coordinates of the point satisfy the inequalities. Okay, so like this point 2, 0, if x is 2, y is 0, it satisfies this inequality here. Okay, so that's why I get this red region here that corresponds to this inequality here. Now, what's the intersection between the blue region and the red region? Well, of course, the intersection is going to be this triangle here. So it's going to be this triangle. So that's my region. That's my region of integration. So I'm going to integrate over this region here. Okay. Now, so this region again corresponds to y between 0 and 1 and x between 3y and 3. Now, if I change the order of integration, so let's say I start with x. So my x here, my x would be between So for this triangle here, so my x would be between 0 and 3. So x between 0 and 3, all right? Now y, well, y is gonna be between this line here, the line y equal to 0, and below this line here. Okay, so y is gonna be between 0 and this line here, and that line, the equation of that line is of course y equal to x over 3. So I'm gonna have x over 3 here. Okay, and you can check that this, so the corresponding region to this inequalities here, x between 0 and 3 and y between 0 and x over 3, it will be exactly our triangle here. Okay, so now so what I'm saying is that now I have my e to the x squared. My x is between 0 and 3, so it's between constant. My y is between 0 and x over 3. So we integrate first with respect to y, because y is between functions. So here dy first, then dx. So y is between 0 and x over 3. And my x, of course, is between 0 and 3. My x is between 0 and 3. So you see here, guys, so be careful here. So we have y between 0 and 1, x between 3y and 3. But so if you change the order, then you get x between 0 and 3 and y between 0 and x over 3. Okay. So now let's integrate this. First, we're going to integrate with respect to y, right? And e to the x squared, x is a constant, so e to the x squared is going to be constant, and the integral for constant with respect to y would be constant times y. So that would be e to the x squared times y. And y between 0 and x over 3. Okay, here I have 0, 3 dx. Now, what's this? So now let's just replace, we're going to replace y by 0 and y by x over 3. So that would be integral from 0 to 3, e to the x squared, replace y by x over 3, so that's x over 3 minus, and then replace y by 0, so times 0, and then dx. So that would be integral from 0 to 3. You're going to have x over 3, e to the x squared, dx. Okay. Now, is it possible to integrate this, x e to the x squared? Yes, because, so let me just remind you guys. So if you have integral of f prime e to the f, so what I'm saying is that derivative of e to the f of x, it's f prime e to the f, right? F prime e to the f. So if you have integral of f prime e to the f dx, so that would be e to the f of x plus a constant, of course. So if you have integral of f prime e to the f, that would be e to the f plus a constant. So here, this is my f. So what's the derivative of f prime? That would be 2x. But here I have x over 3. So I'm going to multiply here by 2 over 2. So now the integral of e to the x squared 2x, that will be e to the x squared. So that will be equal to e to the x squared, but then you have this 2 times 3, so that's over 6. X between 0 and 3, so you replace x by 3, so e to the 3 squared over 6 minus e to the 0 squared over 6. So that's e to the 9 over 6 minus e to the 0. 0 squared is 0, e to the 0 is 1, minus 1 over 6. So that would be the answer. Okay. Yeah, so actually this is a really good example. Like I really like this example. Okay. And yes, so now let me say a couple of words about the triple integral. Okay, so in the case of triple integrals, well, there are three different scenarios, basically, three scenarios. Or three cases. Scenarios. Here, sorry. Scenarios. Okay, or three cases. So if, first case, if you have your function, your z between, let's say, f of xy and g of xy, okay, then you're gonna have, so triple integral, then you start with the integral of with respect to z. So here's, you have your dz here, okay, and then you put your f of xy here, and here g of xy. And here, let's say here you have some integral. So this is h of x, y, z, okay? And then, because, so you see, so z, if your z, let's say if your z is between two functions of x and y, so first you integrate with respect to z, and then you integrate with respect to x or y. Let's say here is dx, dy, or dy, dx, depends actually. So you, let's say your y is between, here y is between functions of x. So let's say here y is between u of x and v of x. Then that will be u of x here, v of x. So here, and then you have dx. So let's say your x is between two constant a and b. And of course, if, so here guys, if your x is between two functions of y, and y is between two constant, then what you do, you need to, so if, so what I'm saying is if x is between two functions of y, okay, I have v of y, and y between two constant, let's say c and d, then you need to change the order. So that will be like, here's dz, then dx, and then dy, okay? And then you have your function here, of course, as usual. So that will be your order of integration. The point here, guys, you need to, so the last integral, it should be, the bounds of the last integral should be between constant, okay? So you can end up with a number, because again, this integral is supposed to, you know, be the volume, the volume of some solid. So it's a number. So you don't want to end up with a function of x or a function of y. So you need to end up with a number. And if you want to end up with a number, the last bounds of integration, they should be constant. Okay, so you always finish your integral, the bounds of the integral, the last bounds of the integral here, they should be always the constant, okay? The second scenario, of course, if you have, second scenario is like if you have y between two functions of x and z, g of x and z, then of course you start with integral with respect to y. So here should be f of x z, and here g of x z. Right here you have some function of x, y, z, and then as I said, here it depends if you're depends. So so it depends if if your x is between two constant, then you can you finish the last integral should be the integral with respect to x. So here you have two constant, let's say, but if your z is between two constant, you can just finish your integral with the integration with respect to z. So the bounds here, again, the last bounds here should be constant, okay? And the third case is when you have x between functions of y and z. And again, the same thing. So if your x is between two functions of y and z, then you need to start your integral with respect to, first integral should be with respect to x. Okay, and then of course here the order depends if your y is between two constant or your z is between two constant. So if your z is between two constant, then the last integral should be with respect to z. If your y is between two constant, then your last integral should be with respect to y, okay? So here, again, this is f of yz, and here g of yz. Okay, let's do an example so we can see what I'm talking about here. An example. Let's say you want to find the volume of the solid enclosed by the paraboloid z equal to 1 plus x squared plus y minus 1 squared, and the planes z equal to 1, x equal to 0, x equal to 1, y equal to 0, let's say, and y equals to 1. Okay. So here from the problem, guys, you can see, so your z is between the plane, the paraboloid. So so here you have some paraboloid. Let's say this is your paraboloid, okay, and so this is your paraboloid, and you can see from the equation of the paraboloid, so 1 plus x squared plus y minus 1 squared, so the squares is always positive or 0, so this number here is always larger than 1, okay, this is always larger or equal to 1, right? So I mean, if x, of course, is 0, y is 0, then you get 1, right? Otherwise, it's going to be a number, if x is 0, y is 1, then you're going to get 1. Otherwise, you're going to get a number which is larger than 1. So this is always larger or equal to 1, right? Because it's 1 plus positive numbers, or 0. So your z is between 1 and 1 plus x squared plus y minus 1 squared. So z equal to 1, that's it's not equation of a line, it's equation of a plane. Z equal to 1, that will be this horizontal, let's say this horizontal plane here. This is the plane z equals to 1, okay? Your x is between 0 and 1, so x is between the planes 0 and 1, and y between the planes 0 and 1. So that would be something like, let's say, so the region would be this one here. Let's say here's some region here, supposed to intersect here, some region here. Anyway. So you want to find the volume of the solid. So you see here your z is between, y is between constants, so that's good. X is between constants, so that's good. Now your z is between 1, and here you have a function of x and y. So your z is between a constant and a function of x and y. So when you integrate, the first integral should be with respect to z, because your z is between functions of x and y, right? So the volume, remember guys, we said by definition, the volume of the the solid. So in the triple integral, we said that's the triple integral of 1. Okay, so if you compute the triple integral of 1, that will be the volume of the solid. And of course, because z, as we said, z is between functions of x and y, so we integrate first with respect to z. So here we need to put z. Then both x and y are with respect to constant, so it doesn't really matter here the order. We can do dx and then dy, because both x and y are between constant. But for example, let's say y is between functions of x and x is between constant, then after z you need to integrate with respect to y, because y would be between functions of x and then x between constants. So you finish your integral with the dx. Okay, so here dz is between 1 and 1 plus x squared plus y minus 1 squared, x between 0 and 1, y is between 0 and 1. Okay. So first we integrate with respect to z. It's just 1, right? Constant 1, you integrate with respect to z, so integral of 1 with respect to z is going to be just z. So that's z between 1 and 1 plus x squared plus y minus 1 squared, dx and then dy. So you replace z by 1 and then z by 1 plus x squared plus y minus 1 squared and then by 1. So that will be the double integral, 0, 1 here, 0, 1 here. So it's 1 plus x squared. You replace z by 1 plus x squared plus y minus 1 squared minus, and then you replace z by 1, so minus 1. Okay. And then you have dx, of course, here. You have 1 minus 1, so 1 minus 1, so it cancels out. So it's just, now it's just double integral from 0 to 1, x squared plus y minus 1 squared, dx, dy. So we're going to integrate with respect to x, integral of x squared, that will be x cubed. So we're going to be x cubed over 3. We keep the 0, 1 here. Plus integral of 1 y minus 1 squared. I mean, y is a constant. Constant minus 1 squared, that will be also constant. And the integral of constant with respect to x would be constant times x. So that will be y minus 1 squared times x. And you evaluate x between 0 and 1, dy. So 0, 1, you replace x by 1, so that's 1 cubed over 3 plus y minus 1 squared times 1 minus, and then you replace x by 0, so it's going to be 0 here, 0 there, and so it's going to be just 0, so it's just minus 0, so it's just 0, and then we have, of course, dy. So that's equal 0, 1, so 1/3 plus y minus 1 squared dy. So integral of 1/3 with respect to y, so that's just constant, so that's y over 3 plus integral of y minus 1 squared. Right. So here, guys, you don't have to expand this whole thing. You can, of course, expand the y minus 1 squared and then integrate. Or you can just say this is actually, the integral would be y minus 1 cubed over 3. And so y between 0 and 1. So now we replace y by 1. So it's 1/3 plus 1 minus 1 cubed over 3 minus, and then we replace y by 0. So it's 0 over 3 plus 0 minus 1 cube over 3. So that will be actually 1/3 plus, this is just 0. This is 0. 0 minus 1, that's negative 1 cube minus 1 minus, there's this minus, well, minus negative 1, that's plus 1, so that's plus 1/3. So the answer, the volume of the solid enclosed between or by the paraboloid and the planes z equals to 1, x equal to 1 and 0, y equal to 1 and 0 is actually 2/3. Okay. Anyway, guys, I guess I'm gonna stop here. And you can find actually much more examples. There are a lot of examples, more examples in the lecture notes. I'm gonna stop here, and I will see you next time. Thank you.